Okay, so this is my online recorded video in place of lecture. And remember, we looked at the priority queue and we tried all kinds of list implementations. We tried the list with links, unordered and ordered. We tried arrays, unordered and ordered. And they all had their advantages. Some of them had good time on some of the operations, but each one of them experienced theta of n time for some operation. Then we looked at binary heap, and we did this using a tree, drawn on the slides. And it looked like a tree, and actually is a tree. And what I'm going to do in this video is show you an efficient way of representing that tree in an array. But what we found was that the operations that we needed to do, insert or extract min, on a binary heap that already has n items in it, took theta of log n time, which is pretty good compared to the other implementations. So it's a fairly clever data structure. That's enough there. Let's see. Okay, so what we're going to look at is an efficient way to represent the binary heap. And it turns out if you think about the way in which arrays were useful previously in representing lists, that tended to be the case when we knew the size of the list ahead of time and when insertions and deletions were kind of at one end, like at the end of the array. So this idea of representing the binary heap in an array makes some sense. We know the maximum size of our heap, at least that's true in this class. The elements are always added at the end for insert. Remember in the tree, we had the nearly complete tree property, which insisted that nodes pile in from left to right, top to bottom. And in response to extract min, we're going to take the node from the root of the tree, but then we take the last element in the tree and put it up to the top and then heapify. So there is a lot of action at the last element of a heap. So this array is actually probably a pretty good way to store a tree. And there's just the issue of, well, if it's in an array, how do we keep track of what's a parent and what's a child? And more importantly, for a given parent, who are its children? And for a given child, who are its parents? Turns out there's an easy solution to that for the binary tree. So let me remind you a couple of things about arrays, and specifically the way we're going to be using arrays in this particular assignment and for priority queues. So in Java, arrays start at 0, and that's been true for most languages in the past 20, 30 years. So if you ask for a new int array of 10 locations, you get 10 locations, but they're numbered 0 through 9. We could start filling in the array at location 0. But what we're going to do for the binary heap is we're going to start filling it in at 1. Now there's a couple reasons for that. The text does it this way, and if I were to start at 0, all my formulas for parent and child and all the way that my code would look would differ from what you see in the book, and that kind of inconsistency could cause trouble. Now I'm not really sure why binary heaps start at 1, except that historically computer languages used to begin arrays at 1, and Fortran was an old language that had arrays that always began at location 1. Now the formulas for doing parent and child are a little simpler if you are using an array that starts at 1 instead of 0, but they're not that much simpler. Okay, so anyway, 0 had this is sort of a joke down here, 0 had certainly been discovered by the time binary heaps came along. So what we're going to do is we're going to allocate but ignore that 0th location. We'll just pretend it's not there. And so our arrays will actually start filling at 1. Okay, so it's a binary tree, which means every node has at most 2 children. Some nodes have no children, like the leaves. Some nodes in a binary tree just have 1 child so far, but could fill in later with another child. And it's going to be predictable where childless parents are going to appear. They're going to be near the end, at the bottom row of the tree when we draw it as a tree. So the question is, how do we infer the relationship between a parent and its children? And how do we infer that relationship in the other way between a child and its parent? So the root, which I'm labeling R here, will always be stored at index 1. And given any node P, and let's say we're treating P as a parent at the moment, and it has a left child A and a right child B, it turns out that if P is stored at some index I, and in this example I'm assuming P is stored at index 3, then the left child is stored at twice that value. So node A would appear at index 6 in the array, and the right child is stored at 2i plus 1, so node B would appear at location 7. Let me just do that again. So given any node P, you're wondering, why did I put P at location 3? Well, there could be a parent node at 3. Any node can be a parent. It just has to have children. And to have children, those children will be located at twice the index of the parent and twice that index plus 1, with the left node going at twice the index and the right node going at twice plus 1. Now, if we have a node and want to know who its parent is, we just kind of do the inverse operation of multiplying by 2, and it turns out the floor of n divided by 2 gives us the answer we want. So for example, 6 here, if we divide that by 2, we get 3. And the floor of 7 divided by 3 is also, I'm sorry, the floor of 7 divided by 2 is also 3. And that's kind of a nice thing. If you remember how integer division works from 131, we lose anything after the decimal point. So 6 divided by 2 would always be 3. 7 divided by 2 should be 3.5, but in integer arithmetic, we discard the half and we just get a 3. And so it's actually not so bad in computer science that this happens, because frequently it's exactly this floor of division that you want. So that's kind of nice that it worked out that way. Okay, let's go back to the example that I had earlier in these slides, but this time using an array. So here's the tree that you might have seen. And the root node is going to sit there in location 1 as promised. And if we think about where the next node is going to go in the heap, it will end up down there on, as a child, the left child of 4. And twice 1 is 2. And so sure enough, 4's left child is allocated at index 2, and that's where it should go. The next node, 77, goes at twice 1 plus 1. 2 times 1 plus 1 is 3. And so there are our first 3 nodes in the tree, and they're piling in from left to right in the array, and also from left to right, top to bottom in the picture shown of the array as a tree. Okay, let's keep going. So let's think about the next node that will show up. It's down here, and it's 17's left child. Twice 2 is 4, so we expect it to show up there, and sure enough, it does. And how about over here? Well, that's going to be twice 2 plus 1, which is going to be index 5, and so it fills in there. And this just keeps going until our tree has everything in it that we want it to have. So this is a pretty good arrangement, really, for an array. These nearly complete trees fill in top to bottom, left to right. And with the indexing scheme that we're using in the array, that corresponds to adding just at the end of the array. And that's a very easy thing to keep track of. So this is all I'm going to say about how we're storing the trees. I'm going to record a separate video to introduce the lab that we're going to be doing to you.